Now equipped with the knowledge of what a function derivative is, let us use the idea from calculus to train a linear regression model using a method that is called or related to now equipped with the knowledge of what a function derivative or gradient is, let's now take a look at training a linear regression model using these concepts. Now equipped with the knowledge of what a function derivative and gradient is, let's now train a linear regression model. So this technique in the context of linear regression is now equipped with the knowledge of what a function derivative and gradient is, let's now train a linear regression model. So for this we will be using a technique called gradient descent, which is related to computing function derivatives and gradients. So consider the linear regression model here again, where the activation function is just the identity function. So this is just like a regular linear regression model. And we have one output here. So this is our prediction. And for fitting or finding these weights, we want to minimize the loss or the prediction error of linear regression. For this, we formulate a convex loss function. In the case of least squares linear regression, that's the sum squared error, or we can also consider the mean squared error, doesn't matter. So either one would work. So for this squared error loss, what we have is we have the prediction minus the actual value that we want to predict. So we consider the difference between the two squared. So why the squared? I mean, this way outliers will be more heavily penalized, and also it doesn't matter whether one or the other is on the left or on the right hand side. In any case, so if we would plot this now, by the way, I should say this is over the training examples. So if we have a data set with n training examples, this would go from first until the last training example. So the loss on the training data set. So now, I plotted the loss here at the bottom as a function of one of the weights. So you notice there are usually multiple weights. Here we are looking only at one of the weights because it's simpler to look at, but you can also generalize this concept to multiple dimensions. So what you can see is this bowl shape or parabola shape, and the loss is minimum for a certain value of the weights. So if the value of the weight is too large, you can see the loss goes up, or maybe it's easier to see it like here. If we go to the right, if the weight is larger, you can see it has a higher loss, and the same way for this weight here that is too small. So there is a so-called global minimum that we want to find. So we want to find this global minimum for the weights so that our prediction error or loss will be minimized. We will do that for, of course, all the weights. So if you think of this in 3 dimensions, so if we have this W1 and the second weight, this would be like a bowl, like a cereal bowl or something like that, where you want to reach the bottom of the cereal bowl. But it's easier to think of it as maybe as 1 dimension. Let's now see what happens if we use the concept of gradient descent. So what we do is we have to start with a certain weight. Let's say this weight, this is our starting point. So in practice, for a linear regression, we usually initialize the weights to all zeros or small random numbers. So if I had initialized the weight with the value 0, we would be over here. And you can see also, the loss would be pretty large here at 0. We want to find basically this global minimum. That's our goal. So if you think back, if you have seen the optional video on the derivatives, so this is like almost like the squared function that I talked about, so x squared, right? So, and we can compute derivative of this function. So the derivative of this function with respect to w1. For example, if we consider our starting weight, so this is the weight we currently consider or we start with, let's say this is a small random number, we can compute the function derivative at this point, so here. So, and then Using this, we can, so I should say, actually the derivative should point upwards here in this direction, but this is this arrow here is the negative, negative slope. So this arrow here is the negative slope, and we can use this negative slope in multiple dimensions. You can think of it as a gradient instead of a derivative. We can use this function gradient to guide the weights into the direction of the global minimum. So the slope would tell us how steep the function is. So at a given point, how steep the function is. But yeah, we are interested in the negative slope, which is also giving us the steepness of the function, but instead of pointing upwards, it's pointing downwards. It's pointing towards the minimum that we want to reach. So we can use then this value, this negative slope or negative gradient, to guide the function downwards towards this global minimum. So we make small steps towards the global minimum, one step at a time. And for that we have, as I've showed you, I think in the second video of this lecture, we had a so-called learning rate, eta. And so the learning rate eta, together with how steep it is, guides how much we update. So you can see here at the bottom it becomes a bit flatter, right? So the function is not as steep anymore. So in these cases we also make smaller steps, because the update really depends on the steepness and also on the learning rate. So the learning rate would all scale these slopes by a constant. So the learning rate is usually a constant that scales all of these slopes. That is like an optional step. You don't have to use learning rate, but in practice in deep learning it's kind of required to have a learning rate, and also there will be extensive tuning into what is a good learning rate. So this is something where you would have to try different learning rates and see what performs better. But this is something that will be done later in this class, and I will probably also make a homework about that, where you have to play around with this a little bit. So if you have a learning rate that is too large, what might happen is that you might overshoot. So if you choose a learning rate that is very large, you may make an update. So let's say you make an update here. This is maybe a little bit exaggerated. So you move from this weight position to this one. And then the next update is a large update here. So in this case, the update has been too large. So you're overshooting the global minimum. And depending on what you find here, you may overshoot even more, and then you kind of lose the way, so your loss will increase. You can see that happening in practice if you use a learning rate that is too large. So notice here also I'm only again always looking at one weight, but there are weights in multiple dimensions. So in that way there's a lot of possibility something like that can happen if we use a large learning rate. So it's actually better to make like smaller baby steps towards reaching this global minimum. However, if we make the learning rate too small, it will just take a very long time until we reach this bottom. So we make all these little baby steps. It will take a lot of iterations or a lot of updates to reach this global minimum. In practice, for a convex loss function like this one, where we have a global minimum that is easy to reach because everything is convex, then it's not a problem usually to have a small learning rate. We have to just be patient. In practice, for deep learning, this would be a problem because the algorithm can get stuck. So in deep learning, we usually have loss functions that are not convex. So we can have a loss function. Let me draw you an example. We can have a loss function that is somewhat, let's say, like this. So if we have then a weight where we start here, let's say we go down here, then it goes down here. Okay, this would actually be a good case, sorry. Let's start here. So if we start here, we make small steps, then we may end up in this pit here. This is a local minimum. So actually I made it relatively steep, so you would probably end up in this one eventually anyways, but let me make maybe a flatter one, like something like this. So what could happen is if you have a very small learning rate, you go from here into this pit and then you get stuck here. because the learning rate is not large enough at this point here to jump over this, for example. So in this case, having a too small learning rate can also be a little bit bad. But yeah, in practice, we will later talk about algorithms that have a so-called momentum term and to overcome these little challenges also. Okay, so but moving on. Yeah, here you have the overview of the online mode again, just for reference, to just show you what we want to get at now. So what we want to do is we want to find this global minimum. So just pay attention to the right hand side here. This is the stochastic gradient descent. There's also a batch gradient descent. I will say a few words about that. But here, for simplicity, consider the case where we update one training point at a time. So in this case, what we do is we compute the gradient of the loss function here. So you can see we compute the gradients here. And we have this for W and the bias, and in that case it would be just a partial derivative, not a gradient. But let's use the same symbol, the nabla, for everything. It's, I think, simpler compared to switching between different symbols. So then our update is based on the current weight and then the learning rate. So this is the learning rate again, times the negative gradient. You can see there's a negative now, the negative sign. So this is because we want to go towards the global minimum and not upwards, right? So we don't want to make the loss larger, we want to make the loss smaller. So we take a step into the direction of the negative gradient. So here we use actually these gradients to update. So what are these values? So where is this value and this value come from? Where does these values come from? So for that we can derive our loss function, right? So we can derive our loss function with respect to W and with respect to B. Yeah, let's now derive the loss function with respect to W. So here we are only taking a look at one of the weights, Wj. Just to keep it simpler, we could also do this for the weight vector. But yeah, recall the gradient of the loss would be just a collection of these individual partial derivatives, right? So we would have the partial derivative of the loss with respect to W1, W2, up to Wm. So that would be a vector. So here we are only taking a look at one of these, for example, the first one. Let's call that Wj, some of the arbitrary entries here in this gradient vector. So we are considering here the sum squared error loss. So in the previous slide I showed you for simplicity the stochastic version, where we only update or compute the gradient based on one training example at a time, which would be an approximation of this overall loss function, right? So if I only consider one data point without the sum, so if I ignore the sum, this one would be only an approximation of the overall loss function on the training set. So here, using the whole training set, it's actually more accurate. This is also sometimes called just gradient descent or batch gradient descent if we use the whole training set where we have I equals 1 up to n. And then we can also consider though a smaller case where we only have a mini batch. So if we have a mini batch, if this is, let's say, a mini batch of size k, and k is smaller than n, this would be the mini batch version. This goes back to what I explained at the very beginning of this lecture, where we have this online mode, mini batch mode, and batch mode. How we compute the gradient, it's the same concept, except that here we have this sum everywhere, but you can also ignore the sum, and then it would be for the online mode. Alright, so what we do now is we are deriving now the loss with respect to the weight. Let's take a look here. This is just the sum squared error loss that I have written down again. Now we are differentiating this loss with respect to Wj. So first step is I'm expanding this term here, the prediction. So if you recall how we compute the prediction, it's the weights times the feature values plus the bias, right? So here I'm ignoring the bias. Let's say it's implicitly included in the weights. So we are only looking at everything without the bias just for simplicity. I've actually included it here, but maybe ignore this for now. And then we have the activation function. and the activation function was just an identity function. So I'm just using this one here, writing it more compactly with using vector notation, W transpose X, using vector notation here. So that's what I have here. So I just expanded this one, and now we are using the chain rule to compute the derivative. So the chain rule is the outer derivative times the inner derivative. So here notice so the outer function would be this one basically. So this is the inner in red, and then the squared here would be the outer function. So what I'm doing is I'm deriving now the outer one. This is this part here. This is the outer derivative. Let me write this down using the power rule. And then on the left hand side here, that's the inner derivative. For the outer derivative, we are basically done, so we don't have to do anything on the left hand side. So the left hand side is done. Now let's take a look at the inner derivative. So if we take a look at this inner derivative, we see, okay, there is another chain rule application required, right? Because again, we have different things going on here. We have the activation function, and then there is the value inside the activation function. So let's now consider the chain rule again, where we compute the outer and the inner derivative. So the way I've written it here is, again, on the left hand side, the outer derivative. So this would be the outer derivative, the derivative of this activation function with respect to its input. So the input is this term W transpose X, and then on the right hand side I have the derivative of the inner part. So this would be the inner part. Notice we cancel the minus y because this is just a constant, so this goes away. Alright, so looking at this here, now this term, what if we compute the derivative of this whole term with respect to w, the result would be x, right? So because we computed the derivative with respect to wj, so the derivative of this term with respect to w, let's say wj, because w is a vector, would be xj, because all the other values in that vector would be constant. So this is what we have here. So this is what we have left over if we derive this part. Now we are left still with the outer derivative to do. So the outer derivative, if we compute that, the derivative of sigma with respect to its input is 1. So why is that? Because we have the identity function here, right? So the derivative of this function, so let me write this down. This would be 1, right? So this goes away. So what we are left here with is just xj. So the derivative of the loss function with respect to the weight is y hat. So if I would condense this again, actually it would be 2 times y hat minus y times xj. And this would be the derivative of this loss function with respect to this wj. And in each iteration, when we do the update or the training, we can compute this value and update the weight values, right? So we can use this term now to update the weight. So if we have the weight, we update it by itself plus then the learning rate times the negative version of this whole part. This would be how we update the weights in each round to minimize this loss function. So here I have an alternative notation of this whole thing. This is actually what people do in practice. So usually to make this a little bit more stable in terms of the learning rate, so that the learning rate doesn't depend on the size of the training set, we actually compute or use the mean squared error. So here we have now a 1 over n, so just averaging. The rest is all the same, except that I now have this 1 over n. But also notice that it's not only 1 over n, it's over 2n. And again, this is really to make things more convenient, because then when we use the power rule, so if I use the power rule here, the 2 goes in front, right? So I have 2 over 2n, and then the 2 cancel, and then I'm just left with 1 over n. And this is a little bit more convenient. So this one is usually the one that is used in practice, because then if I use this one for updating the weights, I can choose a learning rate that is independent of the size of the training set or independent of the size of the mini batches. Otherwise, if I change my data set or my mini batch size, I have to find the learning rate every time from scratch again. Actually, it's important to find the learning rate for each new data set anyways, but if we play around with different mini batch sizes, it would be more robust if we use the 1 over n. This is usually what we do in practice. Yeah, so here's how gradient descent looks like for a loss function with... Yeah, so here's again how gradient descent looks like using a surface plot. So here we have again the mean squared error loss, and we are looking at 2 weights now, and the global minimum is here in the center. Now suppose we start with a weight here. Let's say this is our starting weight. And the lines here, these contours indicate how large the loss is. So of course, yeah, the closer you get to the local minimum, the smaller the loss. And that's where we want to get at. We want to get to the global minimum. Now if we use the batch gradient descent, where we derive the loss function based on the whole training set. So let me just quickly write this down here again. So if we compute the derivative of this one with respect to the whole, or considering the whole data set, then we will make direct leaps towards the global minimum. So each update will be perpendicular here to the contour lines. If we use something like stochastic gradient descent, so that is if we only update based on one data point at a time or based on a mini batch, then the updates will be a little bit noisier. So instead of going straight to the center, there will be like this little zigzag. For linear regression, this is probably not ideal, because why would we want to do that? There's no point doing that. If we can do these direct steps, or make these direct steps, why would we do one step at a time? Maybe one advantage is if we have a very, 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 very large data set, then this will train the linear regression model quicker, because you will be having more updates per epoch. So if you have batch gradient descent, you only have one update per training epoch, and with mini batch gradient descent, you have more updates per epoch. However, each update itself is noisier. Again, for linear regression, it probably doesn't make sense to use mini batch gradient descent. But later, when we talk about deep learning, we have non-convex loss functions, so we probably won't be reaching the global minimum anyway. And in this way, using these little stochastic gradient descent updates are actually better than these complete gradient updates. Also one more note about data normalization. So I think I mentioned it before that it is important to normalize the input data so that the features are all on the same scale. So this is not a problem, for example, if we have something like iris where everything is already on centimeter scales, but it's still helpful to make these values smaller, because there will be certain weight initialization schemes. We will talk about this in a separate lecture, how to initialize these weights well. But if we have, let's say, data sets where we have features on different scales, let's say one is something like, I don't know, income, and the one is age. So you have, let's say, age and income as your features, and income is a dollar amount. So let's say you have something like, $50,000 or something per year, and the age is maybe 23 or something like that. So these are very different scales. So one scale is from maybe 10,000 to 10 million, whereas age is between, let's say, 0 and 100. So in this way, what happens, or what the problem is that these contour lines will be more like skewed, so they will be more like elliptic, and then it will be harder to update, because remember, we are computing the gradient of the loss, so that considers all the directions, and then we may make these steps that are not directly pointing towards the they are pointing towards the minimum in a way in one direction, but in the other direction we make maybe a larger leap. So actually, maybe if we overshoot basically, and then we also end up zigzagging. So in this way, it helps actually initializing the weights with small random numbers, but also normalizing the inputs. About the weight initialization, we will have a separate lecture talking about different strategies for initializing the weights well. Of course, for a simple case like linear regression, it doesn't really matter that much, but it will matter when we talk about deep neural networks. So you can really think of deep neural network training as applying the same concept that we talked about in this lecture, exactly the same concept, but to a more complicated network. But we will also be computing the derivative of the loss with respect to the weights, but in the network we have multiple layers and multiple weights. But except that, it's very, very similar. Alright, so then, to end this lecture, let's talk about training a single layer neural network. So an extension of linear regression for classification. So the ADaLine, the adaptive linear neuron.